everybody all over the world with the opening of the 4th Aquaphotomics International Conference. This is our 4th conference. We already made a history. Every conference, we start as tradition with workshop. This workshop this time will be done by 2 of our colleagues, Federico Marini from Italy and Jelena Muncan from Kobe University. I'll give the floor to Jelena Muncan, and she will explain how we're going to proceed this morning. The idea is to make a very easy to understand explanation. The whole idea of this year conference, because of Corona, is to have a bilingual conference, kind of. So we can have so many people from Japan interested in aquaphotomics as audience. So therefore, we do our best, we have done our best to do everything possible to translate the English to Japanese in order for people to learn and understand more. This is possible, and it has been possible, because of the kind sponsorship of Tsukino Shizuku Foundation, the first foundation developed to help and sponsor research in aquaphotomics. I use this opportunity and this floor to express my gratitude. With that sponsorship, it was possible to do the simultaneous translation of today's event. And I hope that it will give fruits in the future. Thank you very much for your attention. And Jelena, the floor is yours.
Good morning, everyone. So, Professor Tsenkova, thank you very much for this lovely introduction. As Professor Tsenkova announced, we're going to now start with the workshop. I'm very honored to start with this workshop, and I'm glad that I can see so many of you coming from different backgrounds, different ages, different interests, different scientific fields, to learn about aquaphotomics. So before we begin, I would like to say that whatever comes to your mind that you would like to ask during presentation, please just put it in the Zoom chat. If it is too bothersome or too complicated for you to write, just record a video with your question. For example, you can take a screenshot of your Zoom video of presentation during my talk, and then you can send, "Oh, this was not clear to me. Could you please tell me how to do this or that?" So conference email is first line, then you can send your questions during chat, and you can record a video of your question and send it. So we prepared this presentation. I mean, my part of the aquaphotomics workshop would be, in some parts, very simple, and in some parts, it might become too complex. The reason is there are many of you who applied for the workshop with no prior background to spectroscopy and other methods, but it is my experience that anyone can learn aquaphotomics. So I want to start with some basic things so anyone can learn and start. And of course, there are many researchers here who I know have encountered obstacles, even though they are experienced. And to those, I would like to offer some of solutions that we found in our now pretty long experience. So today's workshop will be presented by an expert in chemometrics and data processing, Professor Federico Marini, and me. So for those who don't know what aquaphotomics is, we will start with very, very simple. We are using water as a sensor. How can we do that? Well, we utilize a property of the hydrogen bonds, of sensitivity of the bonds which are connecting water molecules. So these bonds rearrange. If you put something into the water, they will arrange in one way. If you put something else, of that component in the water is changed, the hydrogen bonds are going to be shaped differently. So this is what aquaphotomics measures, and this basic principle of changing components, either concentration or their shape, their structure, is something normally encountered, for example, in so many fields of applications, like, for example, disease diagnosis. So hydrogen bonds are what makes water peculiar. And this is why we actually know life as it is. When we zoom in, if we dive into the water and we zoom in on microscopic level how it looks like, you will see that that the water is actually one very, very complex network, a composite of many different water structures, similar to the snowflakes. So we have very, very different shapes of the structures that water can organize. So how can we see these shapes? We illuminate them. So we put the light through our sample, similar to the way the light reflects the pattern of a mesh on the window, and we can see the pattern in the shadow of this network. The same thing we do with spectroscopy. We illuminate the sample, and instead of shadow, we look at something which is called spectrum. So the spectrum on the left, the spectrum on the right, this is what we actually look at. So how does it work? So from the previous slide, you saw we basically have one light source, we illuminate the sample, and we take the spectra. So all these elements are very sophisticated and developed by very, very smart engineers, and they're put into boxes such as this, which comes in very, very different shapes, sizes, with many different types of opportunities for measurements. I will talk about that later. So you have very, very different instruments. Aquaphotomics likes to utilize all different light sources because light of different frequencies actually stimulates the water in a different way. Each frequency means different energy, and water is a system which absorbs the light, this energy, at all frequencies of light. So whichever instrument you have, near-infrared, ultraviolet, infrared, you can do aquaphotomics. But the basics of aquaphotomics start with near-infrared spectroscopy. The spectra of water in near-infrared look like this. So this is a very particular region to use, this particular light, the region of light spectrum, because it is non-destructive. So you can, for example, take the spectra of living human beings, of your hand, of your, or I don't know if you have yogurt bacteria, and it is completely non-destructive. You do not destroy that. So you can observe the life or whatever you're interested in without disturbing your sample. Other parts of the spectrum are not so non-disruptive. In near-infrared, it is very important when you take a spectra to recognize that the spectra look smooth. So this image is what you will actually have to memorize, and you will see it often and often. But in the beginning, when you are not familiar with aquaphotomics or spectroscopy, you simply don't know what your signal means. And this is important to recognize that the water spectra in near-infrared range is presented by these two large bands, which are a combination band and overtone of the stretching band. It doesn't matter at this point what does it mean if you don't know. And you have little two bumps here, and here if you zoom in, you can even see one more bump. So this is something that you should look for in your signal. And at every area of this picture, if you zoom in, it has to be smooth. It has to look very, very smooth. Why? Because the differences in the way the water structure reorganizes are very, very tiny. And the instruments are not perfect, and they produce noise. We have always some unwanted signal. So in order to differentiate between these tiny differences and something that we don't want, the noise, we have to make sure that we have a good quality spectra. So at whichever region here you zoom in, you have to end up with something looking like this. Now, I want to point out that even though near-infrared is not destructive, it doesn't mean it is totally non-disruptive. So when we pump light, when we illuminate the sample, we pump energy, and the spectra will change in response to that. And this is something that you can use. So, as I said, whenever you zoom in, whenever we try to see these tiny differences, you always have to end up with something that looks more or less smooth. So this way, for example, in this graph presents water spectra, pure water, from which one sample of these 5 consecutives that were taken is subtracted. So it still looks smooth, but you can see the tiny absorbance bands of water appearing. These absorbance bands are telling you how the water is shaped on the molecular level. So this is what we call water absorbance bands. In order to see these differences better, we have developed an entire aquaphotomics protocol of analysis. And one of the most important steps is preparing the signal, the spectra for the analysis. This part is called data processing, and I'm now going to give virtual floor, to our Professor Marini from Italy, who, as I said, is expert in data processing and chemometrics and one of the leaders in this field. So he would know the best how to explain. Federico, you can start now. Thank you.
Well, thanks, Jelena, and also for the appropriate introduction to the topic that would spare a few time in the presentation. So I'm going to share my screen now. Well, let me first, just a second, put it in presentation, and then I will go through it. So, okay. I think since I will move from presentation to MATLAB, that it's better that I share the whole screen. It's easier. Okay. So good morning, everyone, or if you are in the other part of the world, good evening or night, as myself. So, and the topic of this workshop would be pre-processing. So I will try to introduce the most common pre-processing strategies that are useful to deal especially with spectroscopic signal. I will set the rationale for why pre-processing is needed, and I will go through the different options that we have for pre-processing a signal, in particular a spectroscopic signal. And I will stop every now and then to do some practical example on how to do pre-processing and what the different pre-processing do. So first of all, why we need to use pre-processing. As Jelena already said, so we are always measuring signals, in particular spectroscopic signals, in order to get information about the systems that we are studying. And normally, we are, let's say, aiming of having information as a sort of getting to know what are the differences between the samples that we are collecting, hoping that the differences in the signals that we record reflect differences in specific characteristics of the samples that we are trying to characterize. But of course, the interesting source of variation that should cause some relevant variability among the spectroscopic profiles that we are recording is not the only source of variation that may pop up in the signals that we record. So the data that we collect with respect to the ideal shape that they should assume may be deformed by, in general, I would call it artifact, but we should call it better sources of spurious variation, so variation that is not of interest for our system, that may be due to different factors, can be physical factors, can be chemical factors, or also environmental factors. In general, the thing is that these spurious variability sources may hinder modeling in general, and in particular, on one way, the predictive performances of the model, and on the other way, the interpretation of the outcomes of the spectroscopic characterization, and therefore they may blur our knowledge about the system that we are considering. That is why, prior to whatever kind of modeling we are interested in performing, we always try, or we always need to introduce a step of signal processing. So signal processing, or better we should say signal pre-processing, because it's something that we have to do before doing any other kind of modeling, is something that we apply to the signals in order to correct or possibly completely remove the contributions of these undesired phenomena. And as already stated when commenting the previous slides, these undesired phenomena may be limited to the measurement noise or whatever other stochastic source of variation that may impact on the signal, of course, to other and various possible sources of systematic errors that can be like nonlinear instrumental responses, problems related with shift, for instance, in the position of peak maxima, or in general, whatever other undesired sources of chemical and physical variation. Of course, depending on the kind of unwanted effect that we would like to correct, there may be different types of correction that one could implement. And the possible tools are many, but generally they are, let's say, gathered into families of pre-processing tools, because of course there are many tools that are available on the market, just to say, to do some specific corrections. So a non-exhaustive list of the possible tools that one could use for spectral correction, but in general signal correction and signal pre-processing, are techniques for denoising, smoothing. Then there can be background and or baseline correction. In many cases, it may be useful to do some sort of normalization when we are not interested in the absolute signal, but we transform our signal to a scale that is a scale of relative intensity. And in the presence of shifts, that is, well, it's not necessarily the case of spectroscopic signal. This is more for other kind of signal, because in spectroscopy, probably when we have shifts, sometimes it's quite of interest for the phenomenon that we are wishing to characterize. But we can anyway use alignment techniques that are just, let's say, removing the sources of horizontal shifts in the signal. And there may be, especially in the case of NIR spectroscopy, the need to correct for scattering effects that normally end up resulting in additive and mostly multiplicative effects on the signal. So in the following, in the remainder of this talk, I will try to scroll to the, let's say, most common strategies for doing pre-processing. And also, I will end presenting some recent proposal that can contribute to, let's say, widen the arsenal of or the toolbox that we have available for doing pre-processing. Actually, Monday afternoon for you, so I think it's the last session of the conference, Jean-Michel Roger will present practical application of these techniques that I will be illustrating in the last part of this workshop. So let's start going through what the different pre-processing techniques may do. So with a family of techniques deal with smoothing of the signal or denoising. Well, smoothing and denoising are different aspects of a concept that is based in general to removing an informative, of course, possibly an informative high frequency variation. So in general, this kind of high frequency variation is the variation in the signal we associate to instrumental noise, but of course, it can also be, let's say, attributed to other unwanted sources of variance. And since we expect that this signal is a higher frequency with respect to the relevant part of the signal, the way that smoothing or denoising is normally accomplished is through some sort of moving averaging. So we take consecutive portions of the signal and we try to calculate a sort of average of this signal as a way of leveling out these effects of high frequency variation. Of course, smoothing techniques, they do work well when the assumption of the smoothing techniques is met. And in general, this assumption is the assumption that reflects the underlying hypothesis that was explained just before. That means that we assume the signal to be smooth or smoother compared to noise. And the other thing is probably it's a more statistically oriented consideration, is that we may assume the noise to be uncorrelated. So that noise in a point there's no relation with the noise in another point of the signal. With this assumption, the most frequently used techniques for smoothing or denoising are the moving average. Moving average just means that I have my signal and I start from the beginning and I take a segment of a specific length and I substitute the signal in the midpoint of the segment with the average of the signal of the segment. And then I move, let's say, one position, my filter, and I calculate an average and I place this average in the middle of the interval and so on. But a most effective and most commonly adopted way of working with smoothing or denoising is a polynomial filtering. The concept is almost the same as the one in the moving average. But the thing is that instead of simply averaging the signal in the interval, what it is done is that we use a polynomial fitting of the signal in that interval, and then the estimate of this polynomial approximation in the center of the interval is the one that is used to approximate the signal in that point. Then we move the window up to the moment when we reach the end of the signal. There are also other ways of proceeding in order to remove the high frequency contribution, and that can be done by using instead, let's say, a filtering either in the frequency domain by use of Fourier transform filtering, or in the wavelength domain using wavelength transform. But what we will see a little bit in detail is the Savinsky-Golay filtering, because it's the one that is, let's say, applied more frequently in the domain of spectroscopy. The idea, it is a moving filter. It means that we start in the beginning of the signal, and then we move this filter up to the end of the signal. And the thing is that it works by approximating locally. It means only considering a limited number of point windows by a polynomial that is of a specified degree. So normally one would use a second order polynomial or a third order polynomial, but of course one can work even with higher order polynomials, but normally considering like the smoothness of the signals that we want to smooth, that then a second order or a third order polynomial will be enough. The idea is that I want to estimate, approximate, or clean or smooth the signal in this point, that is the central point of the window. Then I will define a symmetric window of points around the point in which I want to approximate my signal. And then only considering these points here, I will fit a polynomial of a specified order. And then I will use only the estimate in the central point to calculate the smoothed signal. Then what I do, I just move the window one point to the right, and I repeat the process up to the moment when I reach the end of my signal. So in order to show you in a, let's say, how this filter is working, I will show you in practice what I'm telling. So take my signal. Let's consider a window of 11 points and a second order polynomial to smooth the signal. Sorry, I don't know what happened. Was something wrong? Let me see. Okay. I did it only for first, only for first derivative, sorry. So I will show you the same when we will calculate the first derivative, because I prepared the demo for that. So we will see it just later, sorry. But the idea is like that. You see, this is a signal, for instance, and here I have moved my point here. I want to estimate the signal in this point, approximate the signal in this point. I calculate in this window a second order polynomial, that is fitting my data, and I will use the approximation, that means the value of the polynomial in correspondence of that particular variable, to approximate the smoothed signal. Then what I will do, I will move the window 1 point further, I will calculate a new polynomial, and I will use the approximation in the center point to smooth the signal in that point. And what I will obtain is a smoothed signal. Of course, the characteristics of this filter make so that we have two parameters on which the smoothness, or let's say the approximated signal, the pre-processed signal will depend. That is the width of the window. Of course, the wider the width of the window that is used for smoothing, the smoother the signal. But the thing is that, of course, it is always a compromise, because if we smooth too much, we may lose the fine structure of the signal. So we should always be able to distinguish between, let's say, a signal that has to be smoothed and the higher frequency contribution that can be relevant because a part of the fine structure of the signal itself. And the other thing is the order of the polynomial. Of course, the lower the order of the polynomial, the smoother the signal. But this is also, you see here, second order, third order, and fourth order, of course, would give you a different adherence of the fitting line to the point. But sometimes, of course, one can have the risk of fitting too much noise in raising the order of the polynomial. So it is always a compromise that should be considered when dealing with such kind of pre-processing techniques. Another kind of treatment is detrending. Detrending is used to remove from a signal a trend. And it can be used, for instance, for baseline correction, if we may think that we have a baseline contribution that is not zero, and in general not constant, and that has to be removed, for instance, through a polynomial fitting. The idea is just to use all the available data to fit a polynomial function, and this polynomial function would be the trend, or let's say the baseline, that will be removed from our signals. Eventually, after I am fitting this polynomial function, I remove it from the signal and I obtain the detrended signal. So let's see it in practice also in this case. So let's consider, let's say, the first signal in this data set, call it x1 is xp. Okay, so this is my signal. And let's see what happens if I want to remove from this signal a linear baseline. So what I should do, I should fit all this data to a dependent variable that is actually a wavelength scale. I can use the original wavelength scale. I can also just use a progressive number scale. So here I would create, let's say, 3,112 wavelengths. So I will create a vector that's from 1 to 3,112. So let's say L is 1 to 3,112. and I calculate a linear fit between my wavelength scale and the signal. So you should imagine that what I'm having here is something like that. And this X1. This is my data. And what I would do, I would try to fit a straight line between this data. So my wavelength scale is the X and my signal is the Y. And I would go to fit a straight line around here. So let's do it and do it easily. How did I call it in the thread? M. So M is made of and the coefficients, I call it P. So P is equal to pseudo inverse of times. Okay. So my correction then is given by my scale. This is linear for the moment times the parameter. So let's say the baseline is equal to M times P. So let's see once again the signal. This is the X1. This is my signal. And this is the linear correction that is removed. So it means that when I do detrending, I will remove this linear trend if I use linear detrending from this signal. So X detrending is X1 minus this baseline. Okay. So this here is the detrended signal if I use a linear detrended correction. Of course, I can decide that here I see a curvature and I can use a quadratic correction. The only thing I have to do is to add a quadratic term to fit a parabola. So M this time is equal to this and L prime. P is equal to the parameter. Here times P. You see that now, like the estimated baseline as a curvature, it's a second order polynomial. And then if I subtract this from the signal, I obtain a detrended baseline with quadratic detrend. That is this one here. So which considerations can we do in this case? The thing is that, of course, detrending as it is implemented is a relatively simple and straightforward approach to baseline or trend correction. But the thing is, but it has drawbacks, because as you have seen, the idea is that detrending, it fits this polynomial trend to all the points. It doesn't consider that some points may be signal, and so they may not be relevant in defining the fit of the baseline. So the thing is that it works only in the cases when the largest sources of variability is the baseline or background interference. Because in other cases, it may remove variation that are interested in all the case that they constitute a reasonably high portion of the variance. Luckily for us, of course, this is the simplest implementation of a detrending correction. Of course, that can be improvements in different ways. One thing is that, of course, this polynomial trend may be fit only to specific sources of the signal. So only to the sources that can be reasonably attributed to the baseline. So this is something that is called, let's say, selected or local fitting of the baseline. Of course, the problem in this case is that we have to know a priori which portions of the signals are baseline and which portions of the signals are relevant part of the signal. That is not always straightforward to do. As an alternative, there are possibilities that are normally based on weighting least square. So weighted fitting, that means that the different points are given a different weights in determining the fitting of the baseline, depending on how likely they may be part of the baseline or part of the signal. This concept has been implemented first in the penalized asymmetric least squares algorithm, where iteratively the algorithm based on the position of the point with respect to the fit, the algorithm gives a different weight to the points of the signal in terms of probabilities of being part of the signals or part of the baseline. And also, you would see it in the VSN algorithm that is proposed and by us, and that will be presented in the end of this workshop. In this case, the procedure gives you a sort of automatic way of estimating some weights for doing the correction. So there are ways in which, if one wants to remove a polynomial trend, can do it based, let's say, on some weights that are empirically estimated from the data. Another important instrument in the toolbox of spectral preprocessing are spectral derivatives. Spectral derivatives, of course, are derivatives of the signal and allow, as a first thing, to remove constant or linear offset from the signal data. And you see, this is a kind of image that is always reported with similar barrier or with similar aspect when like minimum variation in different spectroscopic textbook that show that when you have a signal that is made that may contain with respect to the interesting part some additive, that's the red part, and some additive plus multiplicative or linear, let's say constant plus linear offset, they can be removed by derivation. With first derivative, of course, the constant term is removed and the linear term is transformed to a constant. And with second derivatives, they are both removed. Of course, what we gain with derivatives, we gain that we remove these obnoxious effects from the signal. And of course, since, as you see, we get, let's say, a finer structure of the signal, we also implicitly may accomplish at least a partial band deconvolution in the case of highly overlapping peaks. But what we lose when we are calculating derivatives? On one hand, of course, the interpretation may be less straightforward, because when we look at first derivative, and we know it, but we can see it also here in a very clean example, we know that the maximum of the original peak corresponds to the 0 point of a first derivative. Because the first derivative has a maximum when the signal has maximum slope, but crosses the 0 when the signal has a peak. In this case, we have a better advantage when we consider second derivative, because second derivative, due to the nature of the derivative, have a minimum when the original signal has a maximum. So at least, let's say, the position is kept. But of course, we always have to pay attention, for instance, when we do PCA or PLS modeling on the data that we pre-treat with this kind of treatments, because of course, when we interpret loadings or weights or regression coefficients, they will, let's say, be affected by the fact that the signal has this nature. Other drawbacks, of course, is that with derivation, the scale is decreased, and in general, since we do numerical derivation, the noise is increased. So the signal to noise ratio is overall decreased when we do differentiation or derivation. And this is why, in practice, like the spectral derivatives that are numerical derivatives are always preceded by smoothing. And in this context, of course, the most common way of calculating derivatives in practice is by the use of the Savinsky-Golay approach. That is exactly the same as we have seen before for smoothing, because Savinsky-Golay differentiation is just Savinsky-Golay smoothing plus analytical calculation of the derivatives. This is quite easy because since we are locally approximating our signal with a polynomial, once we have calculated the approximating polynomial of our point in that interval, then the derivation is immediate because it can be calculated analytically from the parameters of the polynomial. And this, of course, helps to, let's say, limit the decrease of the signal to noise ratio or the increase and magnification of the noise. And now I can show you the procedure because with the demo that I wanted to show you before, so of how this moving filter averages go. So let's calculate the first derivative with a say 13-point window and the second degree polynomial approximation. So you see here that this is the window of it's 13 points to the left and 13 points to the right in this case. And we approximate always the signal in the central point, that is the red part. You see that we start from the beginning of the signal, the window is moving, we fit a quadratic polynomial here, and in this point, the central point, we calculate the derivatives, and this is how the derivative of the signal is built progressively at each step of the moving window, only the central point is added here to calculate the derivative of the signal. See, in some parts, the smoothing effect is higher. This was a particularly noisy region in this signal. But you see that, for instance, you can also check that actually the polynomial approximation is, in this case, the quadratic approximation for this signal is, let's say, almost, it's good, it's quite good almost at all points so far. Okay, and then of course it will continue. Now, of course, this demo is made to show you step by step the effect of the calculation of the derivative. The good thing of the Savitzky-Golay algorithm is that it's computationally really effective. So you can differentiate even very large data sets in less than a second. So now, in this case, the time of the demonstration is mostly due to the graphical part that I have implemented to show you how the Savitzky-Golay differentiation works. We can quit it for the moment. Okay, other relevant pre-processing techniques are those that fall within the domain of normalization. In general, normalization means moving from an absolute signal scale to a relative one. And of course, one can ask, when is normalization needed? Well, normalization may be needed when, of course, for instance, peak intensity or area are proportional to concentration, but you cannot use or measure exactly the same amount of matter for each sample. Or if you want, you cannot have a constant optical path. Or if the intensity of the signal is affected by unwanted physical or chemical variability that can be due to different, let's say, phenomena like a different amount of water, temperature, particle size, or in conditions in which the acquisition conditions may be different from sample to sample. Normally, of course, the tricky part of normalization is to select what to use for normalizing the signal. In general, signals can be normalized to unit length or unit area. That means either to the norm of the signals or the sum of the intensity of the signals, a sort of the interval of the signal. They can be normalized, for instance, with respect to the maximum intensity, or possibly, and that would be the optimal case, according to a reference signal that can be a reference and well-resolved peak or band in the signal that ideally should be present in all samples. And of course, that's a sort of, that can be considered as a sort of an internal standard. So variability can be considered to be uninteresting. And then we go to what is probably one of the most common sources of variability that are encountered in the spectroscopic signal, especially in the NIR region, that is scattering. In this case, scattering may have an effect on the signal that is linear and multiplicative. That means that with respect to what is the, let's say, through underlying interesting signal, which should be due to the chemically relevant sources of variation, the measured signal has an offset, but also a multiplicative contribution. That means a contribution that varies linearly with the signal itself. Then, of course, one of the ways to correct for this linear and multiplicative effect would be to subtract a good estimate of what the offset could be and divide by a good estimate of what the multiplicative constant could be as well. And the simplest way of accomplishing that is through what is called the standard normal variate. In the standard normal variate, the idea is that there is let's say the offset may be estimated well by calculating the mean of the signal. So the mean intensity of the spectrum across all wavelengths, and the multiplicative term can be calculating by means of the standard deviation of the intensity across the wavelengths. So what we would do, let's say this is one signal here. So this is one spectral profile. Then we calculate the mean intensity. Then here for this signal would be this value here. So if I sum up all the intensities at all the wavelengths and divide by the number of wavelengths, I obtain this value here. I don't know, here is about 0.7. And then I calculate the standard deviation of all the intensity with respect to this mean profile, mean intensity. And I use these two parameters to correct the spectrum. So I take the original spectrum, I subtract the mean of this original spectrum, and I divide by the standard deviation of the original spectrum. So standard normal variate is nothing more than an autoscaling performed on the rows of the spectral data matrix. In chemometrics, normally when we have a matrix of data, for instance, a spectral matrix, we perform autoscaling across the columns, but SNV is performed across the row. A close parent to the SNV correction is the multiplicative scatter correction that has the aim of removing additive and multiplicative effect. But in this case, the idea is that we can approximate the effect of scattering or the general effect of a multiplicative and a linear and an offset, multiplicative effect and an offset can be, let's say, estimated with respect to what is considered to be a reference spectrum. So the idea is that any of the signals that are in a spectral data matrix are aligned or are normalized in terms of scattering or of linear and additive terms with respect to a spectrum that is taken as a reference. And this spectrum is normally the median or the mean of the overall data set. So already we see a difference in SNV and MSC and multiplicative scatter correction. And this difference is related to the fact that in SNV, I can do the pre-processing individually on the signal, on the single spectrum without any reference to the rest of the data set. Because I just take the spectrum, I calculate its mean value and its standard deviation, and I do the correction. Whereas, and this is particularly important when doing, for instance, modeling or cross-validation or whatever, when I do MSC, I need a reference, and to calculate this reference, I need to have the full spectroscopic data set, because I'm normally calculating this reference as the mean or the median of the set. Then what I do, I fit my spectrum to this reference, and I use the parameter of this fitting to calculate the inverse transform. So let's see it in practice. Let's consider that our reference xref is the mean of the data set. So let's see. Okay, here in this case, you see there are some differences, but they seem superimposed, but they aren't. There are differences between the signal and the reference. So what we do is actually something like that. So we point by point use the reference signal as the X and our signal as the Y. So we see it like this. Its reference as the X, our signal as the Y. And you see that they are quite well aligned. They are not perfectly aligned. Here you see there are some points that are not that are deviating from a linear trend, but overall, depending of course on what's the nature of the signal, I have more or less a signal that can be fitted by a straight line. So what I'm doing, I am calculating the straight line that fits this trend, where the point on the X are the points, the wavelengths of, well, the signal at the different wavelengths of the reference signal. The points on the Y are the data of the sample, and I calculate this fit. And once I have the intercept and the slope of this fit, I use those two parameters to correct the original signal and get the MSC correction. There is something that is called extended multiplicative scatter correction, and this is one of the advantages of the MSC, because I can include in this correction also the possibilities of having detrending, so not only an offset correction, but also, let's say, a polynomial detrending, and even the possibilities of removing contributions from interference sources of variation. For instance, if I want to remove from my signal the contribution of a known interferent, I can include this, this correction into the extended multiplicative scatter correction framework. So time is running, so I will just spend a few words on the future trends, or let's say actual and possibly future trends of pre-processing. So SMV, but we have seen it also with detrending before, have the same problem in terms, especially of interpretation. So the thing is that I am calculating the correction parameters using all the spectrum. And I may have a problem when I'm using all the information in the spectrum, because there are some portion of the spectrum that are not, or that are less affected by the contribution of spurious variation, whereas there are other sources of variation, portions of the spectrum where the sources of spurious variation are more relevant, just exactly like we said about baseline correction. So what is the possible solution? We have already seen it. Calculate the correction only on the portions of the spectrum or the signal in general that are not related. Here I said to Y because it was considered also in case we do predictive modeling, but in general, not related or little related to the variability of interest. And then use these parameters that I have calculated only on a limited portion of spectrum to do the correction, be it normalization, or be it detrending, or be it extended multiplicative scatter correction, and so on. Of course, this is a, let's say, a quite tranchant option. Another option is just to use weighting. So instead of, to use a weighted version of the original data to calculate, for instance, the mean and the standard deviation for SNV, or the parameters for detrending, or the parameters for EMSC. So there is, let's say, there is the hard threshold version. I just identify a few set of wavelengths that I'm considering to be, let's say, more affected by the obnoxious part of variation and less to the relevant part of variation, and use this for the correction. Or there is a smoother version of this correction by including weights that range from 0 to 1, where 0 means that that wavelength is not included in the calculation of the correction parameters, and 1 is that I use it, it contributes at its maximum to the determination of these parameters. And then I use these parameters to calculate the correction that I want to apply to X. The thing is that how do I calculate these correction parameters in a way that doesn't take into account, well, that takes into account the fact that I don't have any idea in principle on which part of the signal is relevant, and well, it's mostly affected by relevant variation, and which part of the signal is less affected by relevant variation. So we exploited this concept. We means myself, Jean-Michel Roger, Beata Walczak, and Jelena Muncan, in an algorithm that is called VSN, Variable Sorting for Normalization, that uses, in order to get non-parametrically and hypothesis-free these weights, to an approach that is called RANSAC, that is random selection. And how does it work? Let's imagine that this is a spectral data set. And a part of these wavelengths are mostly affected by spurious variation, and the rest is affected by unwanted variation. So we start, let's imagine that we want to calculate SNV. So we need two parameters. So we take two spectra at random. What we do is then to select from these two spectra two different wavelengths and feed a straight line to these wavelengths. And then we check which points of the spectra fall within the straight line with a certain tolerance. Then we select two other wavelengths and repeat the procedure. Then we check all the wavelengths that fall in this. Then we do the same with another wavelength. Then we do the same with another wavelength, and we repeat this procedure a certain number of times. at the end of the procedure, we end up with something like this. For the first two spectra that I've selected, we check what is the largest set of wavelengths that are selected in the procedure. So you have seen before that for the given two wavelengths here, depending on, from the given two spectra, sorry, depending on the wavelengths that I'm picking at random, I have a certain number of wavelengths that fall in the interval within some tolerance. You see the tolerance here with the dotted dashed line. Then if I select two other wavelengths at random, I may end up with less wavelengths that fall in that interval within the tolerance. And then if I select two other wavelengths at random, then I may have, like in this case, more wavelengths that fall in the interval with tolerance. So in this case, I select the largest set, and this is saved. Then I pick another set of spectra randomly, and I select, and I place in my memory the largest set of wavelengths that is selected. Then I pick another pair of spectra, and I continue the procedure. Let's say that I do this for here just for the sake of clarity in the representation. I did it 30 times. So 30 times I pick two spectra at random. Normally, you would do this thing, let's say 100 or 1,000 times. And what you get frequency of selections for all these wavelengths. Then if you normalize this frequency as relative frequencies, this represents the weights that we use for each of the wavelengths to calculate the correction parameters. And this is what is called the VSN procedure. Of course, we need something because we have something to optimize. We have to optimize here the tolerance. That means around the straight line fit, what is the range of values that I consider as good to define the set of wavelengths that I want to include in the selection. And what we saw is that a good rule of thumb, it's really an empirical rule, is to repeat the procedure with a different tolerance value and check what is the tolerance value that gives the highest standard deviation in the weights that we use, because this is supposed to be the best set of parameters, the best tolerance to be used. So it's, on our experience, it seemed to work on many data sets that we have analyzed so far. And I will close just with a hint, because my time is going to the end. The problems with pre-processing is always and often how to select what is the best pre-processing. Of course, when we have predictive modeling, we have an idea, or we have a support in the fact that we can try different kind of pre-processing and then select the one that corresponds to the lowest error or the best performances that are usually estimated in cross-validation. Recently, the group of chemometric groups in Nijmegen proposed a strategy based on experimental design for the selection of the optimal pre-processing. But in the literature, it has also been shown that sometimes it's not necessary to select the optimal pre-processing, because one can take advantage to combine differently pre-processed data into a single model. It has been proposed by some authors to do it using ensemble learning, when different PLS models were built using different pre-processing on the same data set. And then, for instance, you see it here, the output, so the final prediction were calculated by averaging the predicted values from the different pre-processing blocks. But another approach would be to examine or to process all the data together by means of multi-block strategies. So multi-block or data fusion approaches are approaches that deal with using multiple data matrices in the modeling phase by keeping the identity of the different data matrix, let's say, identifiable. This is the concept. For instance, you see we have a data set here. We can calculate on this data set some first derivatives or second derivatives, S and V. We can even calculate the VSN model that I was speaking of, and even including the raw data as such. So, for instance, in this example, I would end up with 5 data matrices that share the sample dimension, and of course, that are characterized by being, in this case, differently preprocessed. So we can use multi-block data modeling for processing this data without the need to select what could be the best preprocessing strategy. This is an approach that we proposed recently in what is called the SPORT approach. SPORT stands from sequential preprocessing through orthogonalization, because in this particular technique, we decided to use one specific multi-block approach to deal with this model, that is sequential and orthogonalized PLS. So in sequential and orthogonalized PLS, well, I just give you the details, even if probably, I don't know how many of you are familiar with PLS itself and chemometric modeling, but I would just give you some spot of the concept. The idea is that I calculate regression models progressively, so one matrix at a time. And the advantage of this sequentiality is that I can, let's say, evaluate the incremental contribution. So that means the additional information brought by any additional matrix that I'm adding. And I can do it because when I am inserting the contribution of an additional data matrix, I do it after orthogonalization with respect to the previous model. That means I am removing the part of information that is redundant with the model that is already calculated on the previous data matrices. We also extended this concept using another approach that's called parallel and orthogonalized PLS, creating something that is called PORTO, that stands for parallel preprocessing through orthogonalization. This is rather, let's say, new development. The PORTO article was published like a couple of months ago. So, but the idea that, let's say, the take-home message is that you can also rethink preprocessing in a different way. So normally what we do is that we take our data set, we think of what could be the best preprocessing, and we try to select what the best preprocessing can be, and then we act consequently. With these approaches that we have recently proposed, and that I think of which Jean-Michel Roger will speak in greater detail in his talk at the end of the conference, we just say, okay, maybe it's not necessary to select a priori or what could the optimal preprocessing could be, but a greater and richer amount of information can be obtained by processing the data differently preprocessed, because I can take advantage of the fact that different preprocessing remove different kind of unwanted variation from the data. So by integrating the information from different preprocessing, I can have a more, let's say, detailed look at the nature of my data. With this, I think that I took all my time, and I would just stop my talk here. So first of all, I would like to thank the organizer of the conference for giving me this opportunity to speak. It's really a pleasure for me to be here, despite I cannot be there in person, and to have the opportunity of share with you my views on, let's say, how to do pre-processing and how important it can be. Of course, I'm open for questions, not only now, but of course also during the following days, and either like by mail or message or whatever. And I thank you for your attention.
Federico, thank you very much for this talk. From my point of view, from someone who works every day with Aquaphotomics, Federico's workshop actually presented absolutely all that you're going to need. So it is perfectly summarized knowledge that you're going to need in one place. All the workshop is going to be available for download, and I'm certain you're going to review it lots and lots of times in future. Do we have any questions for Federico at this point? Any? Oh. Well, I guess at this point, no. So please feel free to send questions to Federico on, just put the subject in email that this is related to Federico's workshop, and he will answer later, I'm certain. So, Federico, thank you very much once more.
And good luck for your workshop now.
Thank you. So let's just wish, thank you once more. It is very late in Italy, so let's wish good night to Federico. Thank you.
Thank you. Thank you. Bye-bye.
Bye-bye. So, it is really late in Italy. It is like, I think, 2:30, and he's really sacrificed, I think, his night's sleep to do this workshop, and I highly appreciate it. And as I said, from someone who is doing aquaphotomics analysis every day, about what you saw in his presentation about pre-processing is you're going to need that. So every sentence, every advice that he gave you, you're going to encounter some experience, and you're going to do it. So just download the workshop as soon as it's available, and I'm sure you are going to go back to that workshop very, very often. So now I would like to continue with aquaphotomics analysis after, actually a little bit before and after pre-processing. So in my opinion, I have to say, I don't have a background in spectroscopy. I'm a mechanical engineer. So my original occupation was I was learning to design machines for building machines, like robots, big drills, and so on. So if I could come from that background to something which is so tiny, precise, dealing with molecules, trust me, anyone can do that. If you follow some path that I hope we will now have it described. So what you're going to need for certain is a good instrument. Of course, you can't start aquaphotomics without having spectrometer. You will have to have some accessories to this spectrometer. So depending on the type of instrument, you might need some additional tools like fibers, transmission probes, and so on. You will have to have some software to do calculations, and the basic that you're going to need is at least Excel, something to do averaging and subtraction basics of analysis. There are multiple now softwares which are available nowadays free. They're open source and you can use it freely, like Python, R, and I especially recommend R because Aquaphotomics community developed a special package really adapted for the needs of aquaphotomics analysis. And of course, you have many available commercial softwares, which are a bit costly, but they can very fast do the job for you. The last thing that you're going to need is access to internet and to do search. This is how basically people like Federico ended up. I know that he read a lot, he tried a lot, he probably made many mistakes until he gathered this knowledge that we had the privilege actually to see in one place today. So the basic of aquaphotomics analysis is to constantly zoom in and zoom out. So it has to start first when we want to do some measurement, when we are interested in knowing something about, let's say, our food or our cosmetics, our medications, our body. We have to first think of what we want to do, what we want to measure, and plan the experiment. So whatever you have, whatever your sample is, try to make your samples to have many replicates. So if you have, for example, one water that you want to test, take at least 3 bottles of the same water. Repeat the same experiment, repeat that measurements several days, not several days in a row. You can repeat experiments, for example, today, then after 1 month. It is very beneficial, and the more data you gather, the bigger the data set that you have, that's the better. So make sure also that whenever you do this, the experiments which involve any type of aqueous samples, something that is liquid, to prepare also the samples of pure water. So you have to have at least or distilled water, something that is, let's say, devoid of content. There are no other compounds except water. When you do the experiment, when you plan experiment, try to monitor and log whatever you can. So first of all, when you perform experiment, make sure to monitor the environment. So it would be good if you can acquire a data logger. There are many loggers like that available, which, for example, record the temperature, the pressure, the humidity of your laboratory or the room where you're performing the experiment at every second. And they're very effective, and they're not very expensive. Actually, they're not really expensive at all. The second thing that you would like to have, this is optional, of course, but to measure whatever you can measure else beside the spectra, because that will help you understand your samples and understand your spectrum and connect those different, the information that is coming from different sources into into a good summary. So, for example, currently we are, whenever we do an experiment with some watery samples, we, for example, measure the weight of the sample before and after spectral measurements. We monitor that way the evaporation rate. Then, for example, we are taking the measurements of electrical conductivity, of pH value, of dissolved oxygen, or oxidoreduction potential, many things. You can measure water activity. So whatever you think of, you can measure that can be useful. So regarding the instrument, there are really different instruments available on the market, from very, very expensive and large, like this XDS, which is really the one that we have into laboratories. And nowadays we even have spectrometers which are this size. So that was my experience. For example, when I first came to Professor Tsenkova's laboratory, I used equipment something like this. All the samples of water I would put to cuvette and then put into the instrument and measure the spectrum. When I came home to my home laboratory, and we were supposed to actually open a new spectroscopic lab, I was given an instrument like this. It was this size, and it was like, here is your spectrometer. And I was like, this is a spectrometer? Where do I put the cuvette? So there were really many instruments, many instrumental setups, the fibers that you can use, the measurement modes that you can use, like reflectance, transflectance, transmittance, and so on. There are instruments which make reference measurements, that is, for example, the air during the entire time your sample is measured. And there are instruments which are called single beam. You have to take the reference measurement, the measurement of air of empty spectrometer, basically, before you do them. So the information about how to use the spectrometers is probably going to come from the manufacturer, from that kind of material. But it is important to understand that you can use all of them. It doesn't matter what you have. Do with what you can do experiments with what you have. The important thing is when you start recording the spectra, depending on the instrument and on the acquisition software, your spectra may look very different to what you are accustomed to what you expect to see. So I told you, you would always try to recognize something like this. This is, believe it or not, the only thing that I really could recognize when I left the Professor Tsenkova's lab, and that helped me to fix my instrument, to actually make my instrument work, because when I started recording spectra, I had something like this. I had no idea what that is. So make sure to remember how to calculate absorbance from transmittance if it is measured, and how to calculate absorbance based on the spectral intensity. Some instruments just give you intensity of light which is transmitted to the sample. So it is important to know how to make recalculation. Whatever you do, make sure you end up with something that resembles this. So when you zoom any part of this large spectrum, you should have something like these lines. So this is the visible range, for example. What Federico was talking to you about preprocessing, this spectra shows variations in baseline. So this means that you have to do some preprocessing. This is third and second water overturn range, and so on, and so on. So however you zoom it, you should end up looking at something like this, which is very quite smooth. So make sure always to first check signal quality, to zoom in all the parts of your spectra, and whenever you zoom in something, you should have something smooth like this. When you subtract, for example, average spectrum or something, let's say pure water spectrum, try to end up with this. So make sure to have something looking like this and not like the examples on these images. For example, I had, when I just tested my other new instrument, I ended up with spectrum like this instead of something like this, which meant, in the end, it took me like 1 year to solve this problem. The point is that I was using cuvette, the sample cell, which was quite large in size. So I had to actually diminish the size of the cuvette and to prevent the liquid in cuvette from basically shaking. So if you use the thinner cuvette, it presses the liquid and prevents shaking. The other thing, for example, you must never have something like this. This is definitely a detector problem. So you always have to have a nice looking spectra like this. This is also cut off, which means you cannot have signal here because the detector is too saturated by the signal. It doesn't mean, you don't have to necessarily understand what the saturation of the signal means, but the point is you don't have the signal here. If something like this occurs, if you don't have the first overtone of water, then just use the parts of the spectra that you can. You see, in this spectra, these parts you cannot use. This is the first overtone that we usually like to use. But you don't have this, okay, use the other parts that are nice and smooth, something like this. One more word about spectrometers is that they're very, very interesting. So this is something that we discovered. Actually, not we. Professor Tsenkova discovered a long time ago that when you measure something using light, that near-infrared light influences the water. And whatever spectra you acquire of the same sample, it is going to be different. Water is influenced by light. So since that is the case, actually when we are doing the measurement, we are influencing our samples. That is something we call in aquaphotomics perturbation. And although some people can say, oh, but that means that you can't repeat the same measurements, that's true. But with water, it is absolutely impossible to have exactly the same spectra always. Because, as I said, water is very sensitive. It will change to whatever happens. You can't even notice to what the water responds. So the important part is to recognize that you will always have some kind of perturbation. Even when you do the measurements, you're doing perturbation. And the way the light influences the water during the measurements, or not just water, or your samples, can also depend on the type of light source in your instrument. In that regard, we have so-called post-dispersive and pre-dispersive spectrometers. And I found a very nice image illustrating what this means from one of the manufacturers of this kind of spectrometers. So the difference is that in post-dispersive spectrometer, lamp provides whole spectrum of light. So your sample is really illuminated. In the other type, actually, illuminating is done wavelength by wavelength. So the sample is perturbed by lights of very specific wavelengths, one by one. So the order of these wavelengths is not also the same, so that is something to just have in mind. I know that this might be a little bit complicated, but if you return at later point, you might have already experienced something like this. During the measurements, what is important to do is always start with preparing of your instrument. So scan the sample of, for example, pure water. Or if it's if you're doing, for example, measurements on the skin, you should, for example, first take the reference of it is called spectral or white background. So a reference comes first, then you record something like pure water, something which is we call that dummy sample. So we discard the spectra of the first sample always. Then you start with your samples. So make sure to have samples presented in different replicates. So if I have one type of water, I would like to have one bottle here. Then afterwards, I will record the same water, but from the other bottle. When we put the sample into the cuvette and into the instrument, for example, while leaving the sample all the time in the sample compartment, we are doing something called consecutive irradiation of the same sample. So that is what I called perturbation with light. So you illuminate the samples, for example, 1 to 3 times, or 5 times, 10 times. I like always to use 5 at least, because it helps me do some types of analysis later. So whenever you illuminate, with each new irradiation, your spectra will change. So have that in mind. When you finish your measurements, you're going to end up with basically tables of data, of numbers, something like this. So we will have spectral data set, which is showing you absorbance depending on the wavelength of light. Absorbance of your sample depending on the wavelength of light. The other thing that you have measured, the environmental parameters, pressure, temperature, then properties of your samples that you measured, like electroconductivity, dissolved oxygen, whatever you measured, is going to be another, let's say, table of data, which we called reference data. Now, the point is that you try to join, to match each spectrum, so each sample with its properties. So we are doing this usually by, let's say, manually in Excel, and then put, for example, in some software or so on. But you now have also the available free package, Aquaphotomics, which is developed by Tsenkova and Bernhard Pollner, and it is available from our website. So this software can do this joining for you. So when we finished the measurement, when we combined this table, and when we put the spectra on some kind of plot, we are getting to the part of the first step of the analysis, which is inspection of raw data. We have to take a look at how our data look like. So this is often considered, oh, this is not important, raw data, okay, let's just hurry up and pre-process that. But take a good look at your raw data. It provides you overall inspection of your data set, of seeing what you have. Then it can allow you to detect some spectra that are very strange, for example, and then it can be removed. And from this strange-looking spectra, you can maybe connect that with the things that you measured, so you would understand, this spectra is very different because maybe, for example, temperature jumped, or there was a very, very high humidity in air, and so on. Raw spectra are also allowing you to choose. So based on the observation of your raw spectra, you will have to choose the pre-processing technique. You will have to see, is this spectra, does it look noisy? If it's noisy, you know you will have to do smoothing. If there is a change in this spectral angle that Federico was talking about, then you know that you have to do something like a detrending and so on. So you are making the decision about the pre-processing technique based on the raw data look. And from raw data already, you can see some of the water absorbance bands, so make sure to look for them. When I said raw data can really show you something, it doesn't have to be just bands. For example, we can monitor, this is isosbestic point. What these plots are showing you is the water which actually just passed different phases of mechanical filtration. Depending on the filtration, the isosbestic, the part of the spectra which is not sensitive to changes in temperature, actually is different depending on the type of filtration. So you can see, for example, from the branches of this spectra that they're different depending on the type. Do you see how? So it is already so obvious from the raw spectra, and it tells you something, of course. So these are the spectra of each of these filtrated water taken during heating up and cooling down. And this is also a perturbation that you can use. You can design your experiment to follow that kind of protocol. You can heat it up gradually, take the spectra, and then cool it down. It will show you differences. For example, not just between the samples, but between the samples during heating and cooling, right? There is a very, very good aquaphotomics group in Nanking University from Professor Shao. They are doing amazing things with this temperature perturbation, so I highly recommend to go to our website and see how you can find the related material to Professor Shao's group. And of course, you will have experiences with them during the conference. After the brief inspection of the raw data, we came to the step of data preprocessing. So about that, Federico told you really, at this point, all that you would know to do, to start and to do very good quality aquaphotomics analysis. So the point that I want to make here is that what we are doing with processing might seem a little bit counterintuitive at some points. So basically, as Federico was telling you, you're going to use various types. For example, you can try first derivative, second derivative, to extract those bands to make your signal look smoother. Basically, to remove something you don't want, and to bring out the tiny differences that I was talking about in the water structure. But I want to say, this is something that you do before the analysis, but I always start the analysis with the raw data. Whatever I do first with the raw data, subtraction, for example, other types of chemometric analysis in general, because inspection of the raw data is something that gives you the information of data, of what is the best to use. And for example, this is, as Federico was telling you, you can, this is, for example, different spectra of just two different substances in water. So what you see here is the so-called temperature effect. This means that the basic difference between the spectra of these two solutions are coming from the temperature. Now, from the temperature effect. You can see still in this difference spectra, which is calculated based on raw spectra, that you have these tiny bands of water brought out. But in order to bring them even more together, so you don't have to use, for example, first derivative, second derivative, which target entire spectra in general. You can target, I just want to remove this temperature influence. So in that case, for example, one of my favorite methods for preprocessing is extended multiplicative scatter correction, which he mentioned. So for example, you take this line basically, and in a way you subtract it from the original spectra. So you end up with a different spectrum between those two solutions looking like this. So these bands here they're nothing different than this, only brought better. We can now see it better. That's the basic of what we are looking at, what we are looking for when we are doing preprocessing. So preprocessing really helps. It really brings out water absorbance bands that are of interest. But there is one word of caution here. First, when you remove, as Federico was saying, when you remove, for example, baseline or something, sometimes you remove the information that you need. Like, for example, baseline is telling you if you're doing work with bacteria. Baseline is telling you, for example, about the increase or decrease of the number of bacteria. So baseline do contain information, but it is not chemical related to chemical structure. It's related to something else, to physical information. So sometimes your models, what you're calculating, for example, some regression, can work better without removing, without that kind of preprocessing. Another word of caution is when you're doing preprocessing, so, for example, there is one, and I particularly like this Python module. The point is you can choose various types of preprocessing, do some, let's say, analysis to predict concentration of, let's say, salt in water. And you will, when you're doing that kind of analysis, regression, you're only interested in accuracy, right, of your model. Oh, I can predict with this preprocessing better than with the other. So, in that case, you have, in these cases, you have some information in the end which is valuable and very clear to you. You know, I'm interested only in accuracy of prediction of this concentration. But when you're not looking after something like that, pre-processing, just, you know, trying different types and treating all this process as a black box can be absolutely nonsensical. So do not, when you're doing pre-processing, always look at your data. Always look at what you're going to end up with. Different types of pre-processing are going to give you different types of information. They cannot add, but let's say they cannot really lie to you. But you have to try several of them. You have to be cautious and try to look for the consistency in those results. So in regards to that, so I said, these are two papers that I highly recommend, which are actually a caution tale. They're a cautionary tale about the dangers of preprocessing. But I particularly want to address this standard normal variate preprocessing because I think whenever you had a literature paper or a way to when you read how to calculate aquagram, we would always recommend do the multiplicative scatter correction or SNV. And it is not a mistake, but you have to be careful because standard normal variate can actually distort the spectra. So the good thing about spectral standard normal variate, the point is you should do it locally. You must not do it at the entire range because if you do it, for example, on the whole range like this, you may end up with distortion at the parts of the spectra which are changing differently, which have different offset or different slope. So you end up with something which is showing you the false, not the false information, but the importance. So in this case, importance of these bands may be stressed out when it is not actually the case. So whenever you do something, for example, if you want to use SNV, feel free to just segment your spectra. If you're doing aquagram, just do the SNV on the short part here, for example, and then calculate the point. And especially if you're doing the regression analysis, SNV doing on local SNV preprocessing does not affect your results. It really helps. So the counterintuitive thing with preprocessing is we want to actually make all the spectra as closest together as possible. Because when we, in order to bring them this close together, that means we are removing this physical unwanted source of information, and we can bring out these very tiny differences that we want to know about, which are related to water molecular structure. Now, when we're done with preprocessing, we are coming to the step of spectral analysis. So first, before all the computers were invented and so on, we had the very basics, like subtracted spectrum, average spectrum. And so in that case, even first derivative, second derivative could be thought of as analysis methods, because they are showing you, extracting information. So with spectral analysis, we're aiming at extracting these water absorbance bands. Do not underestimate the power of subtracted spectra, of difference, of helping you finding out about the differences in your samples. So we are very much tempted lately to, since we have so many, different computers, different tools, to just press the buttons and do some calculations and end up with the forests of data. So that approach is like a black box, and you will just end up with lots of totally useless information. So start always, and the good thing about this classical spectral analysis is you don't need anything but, for example, Excel, just one simple software. So first thing, when I do, for example, spectral analysis, I do subtracted spectra, and I do that with the raw spectra. You can see immediately some differences and some water absorbance bands. With the difference spectrum, you can do so many things, so many variations, and each the decision what to subtract from your spectra will help you understand different layers of your samples. So, if you're interested in how, for example, the spectra of some a sick person's blood and a healthy person's blood look like, you would you will subtract healthy from sick. If, for example, you're interested in how your light is perturbing the sample and how how the water is behaving after illuminating, you will subtract, for example, first consecutive. You can always subtract the spectra of pure water and look at the differences of, for example, each water, or I don't know, your samples, for example, which are contaminated, maybe environmental samples. When you subtract pure water, that will show you what's the difference compared to pure water. If you have several types of waters, for example, or just one water which is filtered to different filters, you can take the average spectrum and subtract from all to see what's the difference between those filtering, right? So many types, and all of them can help extracting layers and layers of information. And one of the things that I could highly recommend is subtracting the closest spectrum. That is actually a technique for preprocessing developed at KU University by Dusan Kojic, Professor Yasu, and of course Professor Tsenkova. It is also very adapted to aquaphotomics needs, and especially is useful when you have highly diluted solutions, when you have very low, tiny concentrations of analytes. So after this classical spectral analysis and finding out our new information, we are going to this, let's say, well, this is also spectral analysis, only we call it now chemometrics or multivariate analysis. We are tending with this analysis to actually bring out as much as possible information from the spectra using computers. So different chemometrics methods, different tools are going to be applied depending on what you need. If you need to, for example, classify good from bad apples, good from bad bacteria, you're going to use some classification method like Simca, or there are very different various tools for that. If you want to predict, to model, and to calculate in future the concentration of, let's say, salt, sugar, or whatever you're interested in water, you're going to do regression analysis. So the point is that all these types of analysis you're going to perform depending on the purpose of your investigation, but in order to bring understanding to from a aquaphotomics point of view, you're going to need to look into what is important for this classification, what is important for this regression. And those information can be found in numerical outputs of this analysis, called like loading vectors, regression vectors, and so on. And all this information is providing you water absorbance bands. So from water absorbance bands, the water absorbance bands which we are looking for with all these types of analysis are found as influential variables for making all these models successful. There are other, so these are the basic, and I think aquaphotomics is developed based on these methods. They are quite simple. They're nothing much. They're quite simple to understand. There's so many literature, so I'm not going to go into the details. But the point is, whatever analysis you do, you take all the, for example, meaningful loadings from PCA analysis. It means even if it is explaining, for example, 0.001% of variation, take that loading and look at the peaks, extract the peaks, and put in some kind of table. Do something like that for each of the output of your analysis, because we are looking for the water absorbance bands. There are many, many other analyses that can be tried. For example, one of the fantastic analyses is 2D correlation spectroscopic analysis, or so you have a free software for that, for example. Oh, I didn't provide the link. I'm sorry. So it can be found from, I will give this link later. I'm sorry. I will provide a link later. So this is the free tool, and nowadays there are other, even more advanced methods which are allowing so-called hetero-correlation spectroscopy. This means that you can not only do correlation on spectra gathered from one instrument or one spectroscopic region, but from other different types of spectroscopy. And that is something which are going to, I think, make a really big difference in years ahead. So how do you look for influential variables? Now, there are absolutely now available tools for this too. Influential variable selection algorithms and so on. But the point is, you can do that even without the tools. Just look at those outputs from your analysis, like regression vectors, discriminating powers. Collect all these peaks that you can see. Just make sure you know these numbers. From all these outputs like that, you put them all into one table. So we put all the peaks into one table, for example, from the different spectra back then. I found these peaks to be, quite big. Then, for example, I did the second derivative. I found these three peaks. In PCI analysis, I extracted 4 loadings. There were these peaks in this loading, and so on and so on. You can do that for raw spectra, you can do that for pre-processed spectra, and so on. But build something like this, a table. So from this table, you will see what variables are important based on their repetition. When it comes to this chemometric analysis, I would also advise you to be creative. So, explore how the perturbation during experiment affected your samples. So, for example, these waters that I've mentioned a little bit before in one of the examples, after different mechanical filtration, they showed very different behavior depending on the heating up and cooling down. So, for example, this water is very peculiar. You see, we would expect that we have the same water before and after cooling. We didn't put anything in this water, right? But it is behaving very, this was a pure water, but it is behaving very differently, right? And it's only after mechanical filtration. Then we have a different type of mechanical filtration, and here is the, you see, this water, for example, scores or spectra are going one way when they're heated, but when they're cooled down, they're totally behaving differently. So perturbation is a source of information. Look for the patterns in your data. Look for such kind of relationships. Also, when it comes to principal component analysis, one of the very interesting things is that you can observe your scores as a function of something. So for example, for these waters, I put the scores of second loading as a function of temperature. Because we were heating these waters and cooling them. And I see that I have a very different pattern, like in this second loading vector, in the second principal component. So this also tells you differences, right? And so for example, classical science would never find this out because everything was pure water in the beginning, and then we filtered it. When it comes to regression, with your data, with your reference data, try to regress on everything you measured, even if you end up with a very poor model. So, for example, I cannot predict the concentration of this salt. That can tell you something because you can ask question. Why I can't predict this salt, and I could predict the concentration of that other salt. Or for example, these concentrations I could predict, but these other ranges of concentration I could not. So then why, right? Always ask yourself. So in the case of these waters example, I did the regression on temperature. I wanted to see how they're whether I can predict the temperature of water, and I could predict based on the spectral temperature of water based on with a different accuracy. So then that also tells you something about how this filtering, different filtering, is affecting the water, and consequently would end up with actually influencing, dictating the behavior of this water upon heating or cooling. When, for example, in regression analysis, when I had, for example, some environmental pollutants in water, I wanted to see whether I can detect pollution. For example, for one contaminant, I could not develop regression model. I could not predict, I could not see this contaminant with any of this preprocessing. For the other one, which was quite similar in structure, I could, but only with the raw spectra. And so, for example, lots of people are going to, let's say, stop here if they're doing a photomic analysis and say, oh, it doesn't work. But it is not true. So what this tells you, what something like, let's say, bad result is just like a new source of information, right? So this first tells me that these contaminants are different. The fact that I couldn't build the model for one, and for the other one I could. In this case, I developed a model which is not, reasonably accurate, based on raw spectra. That means I utilized physical information, not chemical. That tells me these guys are actually making some big structures, and these guys don't. That is why I can't see these baseline effects. And I can see this, I can create a model only in this ranges of concentration, and we did this experiment, for example, with the parts per billion. So this tells me when this substance is present in water in this concentration, it builds large structures that can scatter light and allow me to model their concentration based on the spectra. So this is very actually informative. You did not get what you wanted, but you actually got more, right? There is also one thing, for example, I said you can regress, you can do the regression for whatever you measured. So for example, I often do regression on the environmental parameters that I measured for my samples. These are different waters collected from different cities or commercial mineral waters. And for example, I just did the regression. I measured these waters for 10 days, morning, evening, so I had a lot of spectra. Whenever I measured them, the ambiental pressure, the temperature, humidity of the room where I measured the spectra changed. And then I did regression on pressure. I tried basically to calculate the pressure of the environment based on the spectra for each water separately. So this showed me that each water is behaving differently depending on the ambiental pressure. And if you can see, there is one here which is very, very different. I also did similar regression with the temperature of the ambient, and I ended up with regression vectors for each of these models like this. And I could see that the one water is very, very different, reacts to the environmental pressure and temperature changes very differently. And the interesting thing about this water is it doesn't very much react. Its reaction is the smallest. And it turns out that it was from one of the, this is very, very special water from one of the city in my home country, which is extremely polluted. It is forbidden for drinking. It contains lots of arsenic, boron, and iron. And basically, this is not water. There is so much things in this water that it cannot. There are no free molecules. There is no interaction with the environment. That is why this water can kill you. Not today, but if you drink it in 20 years, you will definitely develop cancer or something like that. So by now, what I talked about, I hope that I know that the story became a little bit complex, but if you follow these steps, I think you will have much better understanding of what you explored and of what of how creative actually you can be with the simple tools that you have, like subtractive spectra or simple PCA. So it's just about the creativity in order to extract what you need. Look at your samples from all the angles. So we ended up all this analysis with extracting these peaks, these water absorbance bands. We brought out this let's say, tiny differences in how our samples changed, explained in the terms of water absorbance bands. And now we want to know what is important from all this, because there are many in the spectra, right? So to find what is important, we usually call these water absorbance bands activated water absorbance bands, because they are activated by something. For example, they're activated by presence of disease, they're activated based on the changes in temperature and so on. So this is what we want to monitor, for example, in future. These bands are of interest for us, for example, diagnosis, measurement, monitoring, so on. So we use these activated water absorbance bands to create something you all probably know by now. This is aquagram. As one of the reviewers long time ago said when my paper was reviewed, they demanded that I supply aquagram. They say, it is not aquaphotomics without aquagram. So usually people associate this type of graph with aquaphotomics, and I must say that this is really visually always striking. You can, so after some probably experience, let's say, okay, maybe 2 years of experience, you can see this aquagram and you immediately grasp what it means for your sample. So the majority of papers are presenting, and instructions you can find are presenting how to do the aquagrams and these water absorbance bands in the first overtone of water. However, many of you don't have instruments that provide this region. We have, for example, second region, third region, overtone, the combination band, and so on. So the question is, how can I find what is activated? How can I make aquagrams when I don't have these, what we call VAMAX, right? When we don't do with first overtone. So usually, this is a very, very well-known table with 12 water absorbance bands, actually regions called VAMAX, water matrix coordinates, which means these are places where water absorbance bands are going to be found, certainly, in some of these regions. So usually people even take just one band from this region, for example, 3064, 36, it doesn't matter. But if we don't have these VAMAX, right, what am I going to do then, right? So the point is, you go to your table where you put all these water absorbance bands, and you find those which are constantly repeating in each, whatever you did, so find the ones that are there most of the time. What you're basically looking is consistency. So you can do the count of these influential bands, you can put it on the graph, and then you will see, oh, this band appeared in my analysis like 7 times, 8 times. If I did 8 types of analysis, oh, it appeared 8 times, highly relevant. I will take this. So take the most band like this, and you can do this for any spectral region, right? This is third overtone. You can do that even for the visible, for third overtone, for the second overtone, and so on. Combination band, it really doesn't matter. So when you do that, when you find the VAMAX like this, these activated water absorbance bands like this, you put those as bands on the aquagram, right? And at these bands, you're presenting what we call normalized absorbance. There are many papers which show you how to calculate the aquagram, so I'm not going to go into details about that. What you end up is a water spectral pattern which shows you how water changes in relation to what you were looking for. In relation, for example, if you were interested in whether there is a disease in your cells, or whether the bacteria are, let's say, probiotic or not, and so on. So the key thing is that you don't have to limit yourself to one region. You do you can create aquagrams for any region of the spectra if you followed this pattern. When we end up with aquagrams, we actually, so I know that this is the hardest part. So the hardest part is to know what this means, right? So we have water spectral pattern. We know that this is, for each sample, one spectral pattern. And we see that, for example, these spectral patterns change in response to some perturbation. In this case, this is temperature. So what does this mean? What does it mean to have lines here, to have lines here? What does it mean, actually, to have a line at this point at all? So each of these lines is connected with a certain water structure, the way the water molecules are connected or not, and or not connected, or how they combine into a certain structure, which always have a different functionality. So, for example, if you have water here, that can mean I can dissolve something. I can work with this as a detergent or something like that. Or if I have, let's say, a high peak here, that means, oh, this is like, for example, fresh new contact lens. If the line is down, 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 then it is, oh, something is broken in it. Or that can be done with, that can be done, that can be concluded for each of these bands. So how do we find what is the meaning? So we look for the assignments of these bands. We look what they mean in the terms of water structure, and we look for those things in papers. So in our laboratory, we have an internal, very, very large database of water absorbance bands with their structures and corresponding paper where we found this. So my recommendation is to you also do that whenever you do your experiments. Whenever you find some band, put it in a table like this. And in the future, in the next 2 years, I hope before the next workshop, we are going to provide our table with around 500 bands and meanings in the near infrared, and connected to their functionality on our website. So we are working, and this is one of the projects. So in the future, you can just, for example, type 1572 nanometers, and then you will get all the information in what kind of system it was found, connected to what kind of functionality, and so on. Until we have that kind of table, there is this hard work, and it is basically Googling on Google Scholar and relating your findings, relating your absorption bands of interest to whichever paper you can find, which explains, for example, where it was found, what it meant, and so on. It is so one very important thing is to know that some people really prefer centimeter to -1 or wave numbers. You could see that, for example, in the example of Federico's, the first example. He actually had spectra like in a mirror, and that means that it is just reversed. There in the this is the way how to calculate them. So if you don't find much information about your the meaning of your band in nanometers, recalculate into wave numbers, and then look again, Google that. Add words that are related to what you examined, like starch, kernel, whatever, bacteria. If you don't again find anything, you do the recalculation to fundamental frequency. That means you are going to go to infrared. So usually in aquaphotomics we use for aquagrams first overturn, but the point is it is overturn, right? So fundamental frequency is fundamental band is in infrared. So there are ways how to recalculate this frequency to know what is how to find this structure actually showing itself on a different place in spectra. So you can do, the information about the same structure of water can be found in third overtone, second overtone, combination band. So you just have to do some recalculations and then Google that number in relation to what you find. If you don't find the exact number, because as Federico said, the bands are a little bit, can be shifted depending on your system, on the sample you investigate, pre-processing and so on. So Google numbers which are close to that. And from all the papers that you're going to read, you are going to end up with different types. So in one paper, they will assign to one structure, to different. So you will have really many, many different things. But the point is, you will again find the repetition. And even though if something was assigned previously to something like nitrogen compounds, you can now connect that with your sample and assign that to a particular water structure, for example, water which is involved with the protein hydration and so on. So Google a lot, put all you find information in one file, connecting the band, absorbance band of water, the paper where you found it, the meaning, the assignment that they were provided, and the functionality, meaning in relation to what it was found. Was it, for example, during hydration of some product? Was it during, let's say, drying of apples, or let's say, disease and so on. So in this forest of information, look for consistency and what is meaningful for your samples. This is ending up, when you have this meaning, when you understand your sample, you actually put the meaning into the aquaphotom. This is how you create what we call aquaphotom, which means the finding of the water spectral pattern connected to some kind of information. So immediately when I take a look, for example, for this, on this aquagram, I can see, oh, this was my tap water on the beginning. This was after it was stored for a while in this, let's say, filtration device. This was after only mechanical filtration. This was after reverse osmosis. So this is how you connect spectral pattern to the functionality, or what it actually means. This can be done for, let's say, instead of seeing words like tap water, you can say, for example, cancer, diabetes, whatever you can think of. Or, for example, if it's food, cheese, good cheese, red cheese, yellow cheese, whatever. But the point is that this is water. You're looking at the water. So this is also a place for your contribution. Whatever you do, which I really hope that this was helpful for anyone who is interested in aquaphotomics to be able to start. And whatever you, so this is still uncharted territory, this is the new research. Whatever you find, if you think you made a mistake, ask yourself, why do I think this is a mistake? Ask other researchers. So there are many, many places for your contribution, and this is really needed. It would be very valuable. This is how we develop this science. So in the end, I want to, so we are out of time. I'm a little bit even late, I think, to repeat. Whatever questions you had during this presentation of mine and Federico's, write those questions and send them to conference email, and then on the last day of conference we will answer. There is a discussion, Aquaphotomics post-workshop discussion. We will try to answer as many of your questions as possible. It doesn't matter if at this point you don't have a question. You will have these workshops for download. Whenever you think of, you can record a video, you can send us a text to this address. Now you can do it in Zoom chat. We will take all this. I would like definitely to thank all of you and all of you people that I cannot unfortunately see that you're around the world. I really hope that this was helpful to you. Write to us and let's work on this together. Thank you for your attention. And of course, nothing would be possible without our kind sponsors. So thank you, big, big thank you to our sponsors. Thank you.
Thank you very much, Jelena, for the wonderful workshop. And of course, Federico, who is maybe in a sleep already. I could see that it's not easy. It's not an easy matter, I know, but we are starting something absolutely new in this world, I have this feeling. So we try to match science and technology. We try to match people from different disciplines, different interests, and what makes us together, brings us together, is water, which is the common things between us. So it requires lots of effort to learn the discipline that is not ours, but it's needed in order to understand water. So we started this workshop since the first international conference, and I can see that ourselves, so we are getting better also, and developing more and more and more information and understanding. And I was so happy, and thank you, Jelena, for the wonderful, simple, understandable explanation. I think it was very, very helpful. I think someone like me should be, I feel blessed because if we have people coming like Jelena, understanding and with lots of experience and interest, she loves it, so you can see it. And when there's love, there is success. So I firmly believe that we have to learn from each other. You will see in the program of the conference, we have many different topics from different areas. We could manage until now in each of those conferences to communicate between us, people from different areas, because we learn from each other. I learned this being a member of Near-Infrared Spectroscopy Society. This is very similar example. Aquaphotomics is even more challenging. So, but I think this new age, and probably, I don't know, times like Corona, always have a meaning. So the meaning is to use our time for something useful and to learn more about something that we all need desperately. More knowledge about water. Thank you very much for your attention. So we go for lunch and start from 1 o'clock again. お疲れ様です. Thank you.